me start by introducing the phenomenon of inertial particle focusing. So back in 1961, Segre and Silverberg observed in experiments that when particles are suspended in a fluid flow in a straight pipe with a circular cross-section, then the particles which are initially randomly distributed in the cross-section focus to an annular region approximately 60% of the radius from the center of the circular cross-section. This focusing behavior was then studied extensively, and it was concluded that this particle focusing arises in the regime where the inertia of the fluid is small but non-negligible, and this gives rise to inertial lift forces that cause the particles to migrate across streamlines and focus to these equilibrium locations. Now, when these particles are placed in a fluid flow in curved microchannels, then the focusing behavior changes. So first of all, in a curved duct, the flow itself develops cross-sectional vortices, as you can see in this schematic. These vortices are called Dean vortices, as they were first shown by Dean in 1927. So when neutrally buoyant particles are suspended in a curved duct, the secondary vortices induced by the curvature of the duct can alter the particle equilibria. So for example, as you can see these images on the bottom right, the left image shows the particle equilibria in a straight duct. So we have 9 equilibria which are shown by these colored dots. And the image on the right shows the particle equilibria for the same cross-section, but in a curved duct. So as we can see, the location and the nature of these particle equilibria change significantly once the curvature is added to the curved duct. So I'll describe these images in more detail later in the talk. This phenomenon of particle focusing in curved ducts has found many applications in industrial and medical settings. I'll share one example. As you can see in this image on the left, when a blood sample containing tumor cells is fed into a spiral microchannel, then due to the particle equilibria being located differently for different size particles, one can get a separation between the large circulating tumor cells and the smaller red blood cells and white blood cells in the duct cross-section. Here the cross-section is a trapezoid, but similar separation can also be achieved in a rectangular cross-section, an example of which is shown on the right. Such geometries of curved ducts with rectangular cross-sections are very common, and they have been used extensively in inertial microfluidic experiments. So motivated by this, we have studied the particle equilibria and the bifurcations in them in a curved channel with a rectangular cross-section. The theoretical model that we use for our study is the zero-level fit model, or the ZELF model for short. This was developed by Ha et al., and they studied the particle equilibria and the corresponding bifurcations in a square cross-section using this model. Now we adapt this model to use it for rectangular cross-sections. So this simplified ZELF model is derived from the more complete model of Harding et al. By fitting simple model functions to the force fields. If you are interested in more details about these models and its derivation, then you can have a look at the GFM paper by Harding et al. And our conference proceedings paper as well. But at the end, we get two nonlinear coupled ordinary differential equations that govern the cross-sectional dynamics of a particle under the influence of two force fields. So the first is the inertial lift force arising from small inertia of the fluid, represented by the L term. So you have a R component LR and a Z component LZ. And then the second force is the secondary drag force arising from the secondary vortices induced by the curvature of the duct, which are represented by the D term. So in this model, we have two dimensionless parameters. So we have A tilde and R tilde. So A tilde is a dimensionless particle size, and R tilde is a dimensionless band radius. We know that this model is only valid for small particle sizes, so when A tilde is up to about 0.05. All right, so let me start by showing you what happens in the cross-section when only one of the two force fields are dominant for a 2x1 rectangular duct. So in the limit R tilde goes to infinity, we approach a straight duct, and the secondary drag forces can be neglected. So the dynamics are purely governed by the inertial lift force, which result in 9 equilibrium points, which are shown here by colored circles. So these points are stable nodes in green, settled points in yellow, and an unstable node in red. Now, for the stable nodes and the saddle points, there is a large disparity in the two eigenvalues. So what this results in is that this results in the formation of a slow manifold connecting all the saddle points and the stable nodes. So as you can see from the particle trajectories, a particle starting in the cross-section will quickly snap onto this slow manifold and then migrate slowly towards a stable equilibrium point. Now, in the other limit, when the particle size goes to 0, the inertial lift is negligible and the secondary drag dominates the dynamics. Here, one can completely solve the ODEs in closed form, and you can get closed form solutions. And in this case, it turns out to be these closed curves, which are given by this equation. So very small particle essentially follow the streamlines of the secondary flow vortices along these closed curves. All right, so now let us explore the regime where both inertial lift force and the secondary drag force are important. So we have fixed the particle size to a tilde equals 0.05, and we track the location of the particle equilibria as a function of the dimensionless band radius r tilde. So at a very large band radius of 100,000, we have a situation which is almost similar to a straight duct, and we get the same 9 equilibrium points that we saw previously. Now, as the band radii is reduced to 3,500, the two saddle points near the top right and bottom right migrate towards the stable node on the right. And then as the band radius is decreased even further, we see a bifurcation. So the two saddle points and the stable node, they merge to give a saddle point. So this is a subcritical pitchfork bifurcation. Now, further decreasing the band radius, we see that this unstable node was approaching the stable node on the left, and it seems that they two merge and give two unstable spirals. Now, if one resolves this bifurcation more closely, then one sees that this bifurcation is actually a combination of a supercritical pitchfork bifurcation and a saddle node bifurcation. So combination of those two bifurcations take us from here to here. We also see that the stable nodes at the top and bottom are also coming closer towards the saddle points towards their left. So these eventually merge into saddle node bifurcation as well. And then at even smaller band radius, these unstable spirals, they undergo a Hopf bifurcation and turn into stable spirals, which then migrate towards the middle of the duct. So then at very small band radius, we have these two stable spirals near the middle of the duct and a saddle point towards the right edge. All right, so we now do a similar thing for a 1x2 rectangular cross section. So here at large band radii, we again have these 9 fixed points, but you can see that their R and Z coordinates are swapped because we now have a 1x2 cross section instead of a 2x1 cross section. And then as you see that as the band radius is decreased, here we first get saddle node bifurcations between the stable nodes in the middle at the top and bottom edges with the saddle points towards their left. So they emerge in saddle node bifurcations, and then further decreasing the band radius results in a supercritical pitchfork bifurcation where this stable node on the right turns into a saddle point, releasing two additional stable nodes in the vertical direction, which then go on to merge with the saddle points in saddle node bifurcations. And then as the band radius is further decreased, the unstable node in the middle also undergoes a supercritical pitchfork bifurcation and turns into a saddle point, again releasing two unstable nodes on either side. The saddle then goes on to merge with the stable node in a saddle node bifurcation, while the unstable nodes transition to unstable spirals, which eventually develop a limit cycle at very small band radii. So in conclusion, by using a simple particle dynamics model, we explored the cross-sectional dynamics of a particle in a curved duct flow and observed that at large band radii, we get stable nodes, saddle points, and unstable node, along with a slow manifold for both 2x1 and a 1x2 rectangular cross-section. At small band radii, we get different behaviors for the two cross-section. So we find stable spirals for a 2x1 rectangular cross-section, while we get an unstable spirals with limit cycles for a 1x2 rectangular cross-section. We also observed that for both of these cross-sections, we get a rich set of bifurcations, such as saddle node, pitchfork, and Hopf bifurcations as the band radius is varied. So that's it. Thank you for listening to my talk.